Hello students. In this video, I'll be introducing you to the topic of bases using Lake Natron as the context. So on your screen, you can see two images and I would like you to take a guess if the images you are seeing are natural sculptures or are they real creatures. Now, if your answer was that these are real creatures, you're absolutely right. In fact, these images were captured by wildlife photographer Nick Brandt in the year 2013 on the shores of Lake Natron in Tanzania in East Africa. So he actually found the calcified remains of these birds on the shore and he actually positioned them in this manner so as to bring them back to life in an artistic sense. So the question that we have to ask ourselves is how were these calcified remains of birds formed and why does this happen in Lake Natron and not in other lakes? To understand this, we have to understand the composition of Lake Natron. So Lake Natron, as I said earlier, is situated in Tanzania, and this water in this lake is highly rich in sodium carbonate. In fact, the term natron in French stands for sodium carbonate, but the etymology of this word is actually a bit more complex, some tracing it all the way back to ancient Egyptian. Now, to better understand how does sodium carbonate contributes to the calcification of creatures that we saw earlier, we'll have to first understand water bases. So in our last tutorial, we saw how different compounds ionize in water. Those compounds which released H plus ions in water were termed as acids. In a similar way, compounds which release OH minus ions or hydroxide ions in their aqueous solution are termed as bases. For example, if we add a pellet of sodium hydroxide in water, the sodium ion and the hydroxide ion separate from each other. And that's the reason why sodium hydroxide is considered as a base. Similarly, different metal hydroxides such as potassium hydroxide and magnesium hydroxide can also be considered as bases. I would like you to pause the video here and attempt to write the equation for dissociation of potassium hydroxide and magnesium hydroxide on your own, just the way I wrote the equation showing dissociation of sodium hydroxide. Once you are done, you can continue the video. Alright, so potassium hydroxide ionizes as K positive and OH negative, and magnesium hydroxide ionizes as Mg2 plus and 2OH negative. Now, if you're trying to understand why these charges are different, that's because they are derived from the group number. So potassium is in group 1 in the periodic table, therefore it carries a charge of positive 1, whereas magnesium belongs to group 2 of the periodic table, so it has a charge of positive 2. There is only one hydroxide ion here, that's why you see only one OH minus, and there are two hydroxides here, that's why you can see a 2 here. Now, there is another way some substances behave as bases. For example, taking the context of ammonia, ammonia as you can see does not contain OH minus directly. But when ammonia is dissolved in water, what it does is that it breaks the bond between oxygen and one of the hydrogens and takes a proton towards it. Now, when it takes a proton, the water is just left with OH minus and ammonia changes to ammonium. So here you can see that ammonia doesn't directly release OH minus, but because it takes a proton from water, it forces the water in turn to release hydroxide. Therefore, ammonia can also be considered as a base because even if indirectly, it's releasing hydroxide ion in water. Now, carbonate ions also behave in a similar manner. If carbonate ions come in contact with water, they take one of the protons from water, leaving it with OH minus ion, and because it has taken a proton, it creates HCO3 minus, which is also called as hydrogen carbonate ion. The whole The whole idea behind this slide is for you to understand that some substances do not directly have OH minus, but they can interact with water molecules and release OH minus ions. Therefore, these substances are also considered as bases. Now, within bases, we have a subcategory of alkalis. As you can see the image, the bases here are completely soluble in water. Such bases which are completely soluble in water are considered as alkalis. A few examples of alkalis are sodium hydroxide, the formula of which is NaOH, ammonium hydroxide, the formula for which is NH4OH, and potassium hydroxide, the formula for which is KOH. Now, unlike alkalis, other bases such as magnesium hydroxide are not soluble in water. So they are simply considered as bases but not alkalis. So you have to understand that all alkalis are bases because all of them contain or release OH minus ion in their aqueous solution. But not all bases, like magnesium hydroxide, can be considered as alkalis. It's simply because we can see that it's not completely soluble in water. Well, in case you're wondering what is milk of magnesia, so it's basically an antacid used to treat stomach acidity because it's a mild base. So, just like acids, bases are also all around us and we use them for different purposes. The most common base that we use in the chemistry laboratory is sodium hydroxide, which is not only an alkali but a very strong base as well. Other bases are more commonly used in household for cleaning purposes. Some bases, such as milk of magnesia, are used to treat acidity, and even the sting of a wasp is alkaline in nature compared to the sting of a bee, which is acidic in nature. So, coming back to our original question, how does this alkaline water in Lake Natron cause calcification of animals? So, just as explained before, the water in Lake Natron is very much rich in sodium carbonate because of its geology. This highly alkaline water is corrosive, so whenever an animal accidentally falls into the lake or dies into the lake, not only does the highly alkaline water cause tissue damage, but it also dehydrates the tissues completely. Now, because it dehydrates these tissues, they further do not cause any microbial decomposition because microbes require water to decompose the remains of dead organisms. Because there is lack of water, microbial decomposition is minimized. Now, over these preserved remains, other minerals such as sodium carbonate kind of form a crust which hardens in due course of time and dries. This is what gives them a stone-like or calcified appearance. So it's basically a shell over preserved remains of organism, and this whole process of preservation happens because of the highly alkaline nature of the water, because it causes extensive dehydration. In fact, that's one reason why using soap bars over a prolonged period of time, especially the ones which are more harsh in nature, causes dryness of skin because they have a strong dehydrating effect. So to wrap up this whole tutorial, here are a few questions. I'd like you to answer these questions on your own and show me the answers once it's done. Thank you so much.